Well, thanks. Well, you pretty much took care of my first slide here. So
Okay.
I do want to say thanks to Brian because he did mention going to into operations research. I was in his office and he said, you know, you might want to consider operations research. I just learned about that. And that started my career right there. So I went to U of M and got my degrees. Eventually ended up at GM. I had a few other jobs. I've been there for over 30 years. So retirement is on the horizon. Mostly a research scientist, recently become data scientist is our titles now. And I've done a lot of math modeling and that's what's made that job fun. I'll talk a little bit about GM because I understand this is kind of a career focus for students. GM is huge. You can see some of the numbers there, all the continents. You can learn more about GM at these websites there. Our particular group is called Chief Data and Analytics Office, CDAO, about 150 people. It's large, mostly data analysts and scientists. And we work on, problem framing, which hasn't been talked about a lot here, but that's really important that you're solving the right problem with your customers, typically internal customers you're working with. But we get into data collection and cleaning and understanding what the data really is. And then we move on to analysis and modeling, which is kind of the fun part. I would say it's probably 15 to 20% of the job. And then you got to report results, make it visible, and come up with recommendations that you discuss and explain to your internal customers. And this is just one organization in GM. There's a lot of others using STEM. Brian mentioned engineering and design, but there's marketing and finance and on and on. It's just amazing the areas you can get into and use your skill set. My particular group is called Advanced Analytics Center of Expertise. We're the ACE group, we kind of like that. And about 45 people, masters and PhDs, and we're currently hiring. And projects in manufacturing, maintenance, and I'm just reading this, but it goes on. And I've worked projects in every one of those areas except for the last one. So it's been a lot of fun, a lot of different projects. Find my mouse here. Typically, you join at a level 6. We have these levels as a data scientist, and you can advance through various levels up to level 9, which is a fellow. And you can stay as an individual contributor, we call it, which is, solving, day-to-day real problems, or you can go into management and manage teams of engineers, for example. And I did a little bit of both. I went into management and then I enjoyed it, but I really like to solve tough problems. So I went back to the bench and kept on doing math modeling and data analysis. Things that are important to advance is the impact of your project, typically in dollars, revenue, or cost savings, mentoring other people. Teamwork is a big thing because you need to work with other people, especially your internal customers. Your professional profiles are really important if you want to become a fellow, and that means, in your professional organizations, outside of GM, like Informs, which I'm a member of, they want to see that you've contributed there. Identifying good projects and leadership and being a go-to person, and that's what gets you to become a fellow. It's a great work environment, really bright, collaborative colleagues, all sorts of projects. You may be on a project for at most a year or two, and you're on to something else, and typically you have 2 or 3 projects. One of the things I really liked is the potential for huge impact. I'm not talking millions of dollars. I'm talking hundreds of millions of dollars or even billions of dollars of impact from your work. And that is really cool. And that's real life impact in the real world. And that is very motivating, at least for me. I mentioned professional growth, supportive. Safety is a huge issue at GM. They want to make sure we're very safe and very diverse. It's a big push in GM as well. So we have colleagues from all over the world of all walks of life, it seems. A lot more remote work now. So I've been working at home for over a year and I'm actually more productive. So I think that'll be a viable option going forward. And global opportunities. I mean, you can go to Europe, China, Asia, all over. And many people do, and they enjoy that. I want to get into an example of actually using math. And in this case, it's probability and calculus and math, iterations and all sorts. And one of the things that GM does is makes cars, and they like to make them as fast as they can. And that's called throughput. How many jobs per hour or per day can you get? And here's sort of a schematic of a line where you're loading parts, and they wait in a buffer to get into a welder, and then there's some inspection. RoboGate kind of welds them all together, and there's some more spot welding afterwards to strengthen up the joints, and then you have to do some sealing, and then eventually you unload it. What's the throughput of this line? And what makes this interesting is that they all have different speeds, okay? Maybe the spot weld, is the slowest guy there, and we need to speed him up to get throughput up. And they had different times between failures, exponential in this case. Was pretty good. And, sealing, man, they're failing all the time here. Unloading it hardly ever. Maybe sealing is the place to go, and then here unloading, mean time to repair. Gosh, if unload fails, it's going to take a long time to repair that. Maybe that's where we need to improve things. And scrapping, gosh, that first station up here, load is scrapping a lot. Maybe that's where we need to go improve things. Well, as you might imagine, it's really, really hard to figure this out. And there can be hundreds of stations. And so we need a model to figure this out, okay? And there's a lot of interactions in here, like, if inspect, the guy leaves and he can't inspect, then there's no work getting done, and these buffers fill up and everybody stops ahead, and that's called blocking. And jobs all the way downstream, they work their buffer down, and they have nothing to work on, and they're starved, so there's a lot of interactions. And you got to work on the bottleneck to improve throughput the most, and where is it? So I developed a model to do this, take all this data to figure out, well, where is it? And it's actually inspect. And that never showed up as the big winner of any one of these metrics. So it's challenging to figure out, well, where is that bottleneck? Can you do it with data analysis, or actually, modeling and exercising the model? And so we came up with a method where, soon you could understood how to analyze just two stations, one station, a buffer, and another station with all those parameters in play, and figure out what the throughput is of this two station. And it turns out you can apply that to a longer station. You can start with load and just do these two stations and figure out what that looks like operating as a single station. Okay, now you have that as a single station. Then bring in inspect, okay, as two stations now. This aggregate up here and this one, you can figure out what's going on in this buffer, figure out what this three station looks like as a single station approximately, and then go to the next one and keep working down the line, okay, until you've analyzed the whole line. And that's kind of an approximation, because when you brought in one station, you didn't bring down the whole station, right? But then you work backwards and do something very similar, okay? And you already know what the upstream stations are. And so you iterate going back and forth until it converges, and sort of all the aggregate parameter aggregate parameters of all the stations, including all of them together, and now throughput. So how do you analyze this two station thing? That in itself is a big problem, and that's the whole key to unlocking this thing. So consider just one case where the first station is faster than the second station. Okay, and you're starting with a partially full buffer. So this is the buffer contents right here in the middle here. And so, while everything is going okay, the faster station fills up that buffer. Eventually it gets limited by the speed of the downstream station, right? So it just hangs there. Eventually the workstation one may fail. This is just one case of 8. And now the buffer empties out because the upstream station has failed. And now the second station is starved. Okay, and eventually that station one gets fixed and you start over. Well, if you consider all cases from one repair epoch to another repair epoch, and if you knew the steady state distribution of the buffer contents, you could figure this all out and know that the distribution at this point in time of what's in the buffer has to equal to what's in the buffer at the next repair station. It's kind of a steady state analysis, because I consider all paths between. And so I guessed, well, there's got to be an impulse at 0 and an impulse at full, right? And here's its full right here, and here's its 0. And there's got to be some kind of a distribution of what the buffer contents might be in between. And honest to God, I looked at this for a long time and I just guessed it was a sum of exponentials because there's exponential failures and exponential repair rates. And I figured, well, maybe that might work. And it did. So I want to show you the math, and we're not going to deep dive this, but you can see failure rates in here, which is the lambdas and the mu's are the repair rates, and the s's are speeds and so forth. And all these parameters come together. And if you assume this exponential form of the buffer contents right here, and there has to be some impulses added in here, but this is just a continuous part here, you can actually solve this thing using a lot of algebra, a lot of calculus, and under this assumption, and get all these parameters, believe it or not, throw them in here and figure out what's the expected time, uptime, expected time, speed blocking, and failed, and so forth during a cycle from one repair epoch to the next, you know, from here to here. And you, lo and behold, you can solve for the probability that the buffer is empty at a repair epoch. And then you can figure out, well, what's the expected duration of a cycle as a sum of all these things. And 1 over that is your throughput. Now, I don't expect anybody to understand this, but the point is there's a lot of really cool math and fun in here. You know, there's matrices in here. There's a lot of stochastic processes in here, exponentials, Poisson, all that stuff is in there. It's a lot of fun. So in summary then, we started this project in 1987. It took me about a year to drive all the equations and to validate it. I actually wrote a simulation to validate it, and it was top secret in GM for a while. It took months to validate all this. Does it really work? And to pilot as a team in several plants. It worked. We productionized this in 25 different plants, and now it's all over all of our plants worldwide. We eventually added a simulation now to model more complex scenarios, you know, like paint booths and stuff like that. We saved over $2 billion over 18 years. And by increasing sales, reducing overtime, and cheaper line designs, even the design engineers of the manufacturing lines use this tool as well. So they could design in where they want the bottleneck to be, actually. And we won the 2005 Informs Ailment Achievement Award. That's an Informs award that you may know something about Informs. And I finally got to publish the results. And it's down here if anybody's interested in. So I just wanted to, you know, talk about, you know, the diverse projects that you really get to do cool math. You can work on a problem for quite a while if you want to. You don't have to get something done in the next month, so you can get it done right. And just had a great time using that skill set at GM.
Okay. Did you say you worked on a project for a year?
Yeah,
I thought you were much faster than that. I really did.
Well, I thought I was too, you know, but it took me, I read a lot of literature, you know, it took me a couple months just to understand everything that was done. And one of the papers did not solve this problem, but it gave me an insight to compare these two distributions at renewal epochs, and they had to be the same, okay? That was the insight. And I go, oh man, maybe I can do this, okay? And so, you know, there was a lot of research here. And then to actually do all this algebra, I got to tell you, the document is 100 pages of algebra to kind of figure this all out. I actually assumed a sum of 3 exponentials, and it turns out one of them canceled out and to be 0, which was kind of nice to do this. And then I had to validate this thing. People aren't just going to run with this equation and believe I did this all right. And I wasn't even sure I did it right myself. So I spent a good couple of months of writing a simulation and validating this. And it turns out there's all sorts of special cases you have to check for. Like when the 2 speeds of the stations are the same, you get a 0 divide here. So I had a special case and I had to do the algebra for that and figure that out using L'Hopital's rule, which I had to apply about 3 times to get an answer. So there's a lot of cool stuff in here.
Any questions or comments from the participants or listeners? You want to know more about what it's like to work at GM, or maybe we can bring in Rich in terms of Boeing. Is the pay good when you're an industrial method? Chris, you have a question?
Yeah, sure. Could you give like an example of the type of things your team would work on and what they wouldn't work on, like that might involve statistics? In other words, are there some like research and development teams that will just simply have their own sort of statisticians and engineers who are just sort of, they're just doing it all themselves and they're not using your division?
Oh, that happens all the time. There's, like I said, talent and all these other engineering and design, marketing. They all have their data scientists and data analysts. We're kind of a central group so we can handle some of the bigger problems, okay? And also the longer term problems. You know, in the engineering, design, and marketing, they want answers like in a month. Some of these things take a lot longer to do that. And so the central group can do that. We can take longer time to get things done. So that's a real good question. But
Rich?
we're all over the company. Yeah.
Rich, what do you think? You have comments or?
I actually had a question first about, so you published this, looks like it was close to 20 years after the work started. Does GM keep a tight grip on anything you do and want to protect it as proprietary?
Yeah, that's a really good point. If you do work that's really pushes the state of the art, you go through an IP process, intellectual property process, and that gets, you write a record of invention that gets reviewed by a review board, which is mostly a director, executive directors, and experts in your area. And then they decide whether, you know, it really is an advancement. And if it is, they decide, well, is this going to be a trade secret? And so you can't publish it. And we do have to put a report behind it. Or can we publish this? Or is it going to be what's called a, just kind of published in an obscure journal somewhere? And we do that too. And I almost always get trade secrets. I've got maybe 10 or 15 patents, but it's mostly trade secrets. But after a while, there might be a good reason to publish it because, you know, you have a conference, it's good for your professional profile. You know, we've already moved beyond that technology, like with the simulation that I mentioned. And so I was able to publish it a part of for winning that award. And now it's out there. But simulation is so fast now that you're better off doing that.
What about this question Melia asked about equivalent close to tenure? What about career progression? Jeff, you indicated you go up to some level of fellow, but there is no such thing as tenure that says you're almost solidly locked in, or is there?
If you do well, they want to keep you.
Okay.
You know, it's just, you know, there's no tenure thing in the sense, I mean, if you're into research, I used to be in General Motors research, and you can take a sabbatical and things like that. And a lot of people have, I never did.
Okay.
But where I'm at now, it's less likely. They do value early in your career for you to go to some other division and work there for a while and come back. And that's great because we get ambassadors to other divisions, so they want to work with us more. And they learn other skill sets and maybe want to go into management into a different area, you know, and they could do that. So you come in as level 6, you usually get promoted to a level 7. There are promotions in levels. Once you get to level 8, you get a car, which is kind of fun. And level 9 is, there's only about 10%, you know, eventually get to a level 9. You really have to be a star there, but a level 8 is great. I mean, that's a great, you're doing well.
Okay. Yeah, right? I don't think so.
You don't think so? What?
No, somebody suggested in Boeing, they get a plane.
Oh, yeah. You know, eventually.
We do have like a similar fellowship type program. They're certainly not 10% of engineers, but that is, you're not tenured, but Boeing has deemed you valuable enough that they'd rather you stay there than go work for someone else. And so they basically give you this golden handcuffs.
Oh,
Okay.
yeah, we don't have that.
Yeah. Is the illusion that industry pays better than teaching true?
You know, I think they're comparable. What do you think, Rich?
As an engineer, it's absolutely true. Even if you take into account your, the autonomy you get for when school's not in session, it does pay better. But you lose that autonomy. You're going to start off with getting 10 vacation days a year.
Yeah.
Right, right. It's similar here. Eventually you can get up to like 30 days, 5 weeks.
Yeah.
My son got a bachelor's degree and started working for an insurance company and assessing stuff. And they told him he has 2 weeks vacation. He grew up in a household of an academic, and his father had 12 weeks every summer to think about what he's going to do. And I think my son, after working for 6 months, said, I don't really like this. And he went back, and now he's a professor like his father, teaching and loving the academic life. But there are perks in the academic life, that you sacrifice and so forth. But both of you talk about exciting projects. That's what draws you on, and working in teams and colleagues. And as Jeff pointed out, making a significant difference. I'm assuming they gave you some 10, 15% of that 2 billion that you saved.
I wish,
You wish.
but I got promoted to a really nice level, and
Okay.
and every time you get a trade secret, our company gives you 10 grand, and if it gets used, you get even more. So, I mean, we have
as in a royalty for use or something like that. Is that it?
we had one guy that developed a program that generated transmissions, just many transitions. And he got every single one of them patent. He made more money off those patents than he did off his salary.
Okay. All right. Well, there are outliers in every deal, right?
Yeah.
Okay. One son says, I was wondering if there is a potential for impact that is greater than the company, also like in communities. In other words,
that's a good question. GM is really trying to be green. We're going to go all electric, like you mentioned, Brian. And we do a lot of community outreach works, and so and it's also true that you can, in the sense that if we do good things, it not only helps us, but it helps our suppliers and their suppliers and their suppliers, and there's this chain effect that's like a 10x multiplier. And so by increasing throughput, for example, we increase the demand for all those suppliers, and so it helped all them as well. And we actually, in some of the suppliers, we actually took our throughput analysis and went into their plants and helped their throughput so they could supply not only GM, but other suppliers. So I think the answer is yes in some cases.